Ni hao. That's it for my Chinese, I'm sorry. Thank you, everyone, for being here today to listen for a bit of science and this introduction on gravity waves. So, to talk about gravitational waves, we're going to have to talk about two other things before. The first one is gravity, and the second is black holes. What is gravity? Do we have a way of knowing what gravity is? And about 300 years ago, one man realized that the laws for gravity in space are the same as the ones we have on Earth. The man who did that was Isaac Newton. He figured out a formula that says if you throw something, there it will fall. If you know how you throw something, you know how it will fly, how it will fall. According to Newton, this formula should work on Earth and should work in space. Take an arrow, throw it, apply Newton's formula, it will work. Take a rock, it will work. Take a house, it will work. Take a mountain, not that we can do that, but imagine you can take a mountain and throw it, it will work as well. Mercury, the one that is closest to the sun. This one is closest to the sun, so the gravity of the sun acts upon it in its strongest way. And does Newton's formula work for Mercury? Well, yes, but not perfectly. There is a slight change. It's really, really, really small. I'll give you an idea. If you take your watch, you look at the distance between 2 seconds, and you divide that space by about 60. Let's say half that space, that's the difference between what Newton says Mercury's orbit should be and what nature has it in a century. For about 180 years, scientists have tried to find that reason. Newton was aware of that problem, that he found a formula. But the formula does not tell you what it is. The formula does not tell you what gravity is. Newton actually didn't know, and he looked for the answer all his life. And exactly at the end of his life, he died and did not find. So we had to wait for somebody else. You had to wait for 180 years, during which time all the crazy ideas for gravity were allowed. That's one of the good things about science. When you don't know, you're allowed to have crazy ideas. So, about 180 years after Newton, came one man with a crazy idea. Let me show you the idea. Imagine we are in space right now. You look around you, you see stars, planets, everything. Imagine you get rid of the stars. You get rid of the planets. You get rid of everything that you can see. Everything. So you're there in space, and there is absolutely nothing around you. Maybe, once you get rid of everything, there still is something. And that something is where gravity comes from. Why not? We're allowed to think things like that. So, let's go back with this empty universe, and we put a star back in, the sun. Just the sun, nothing else. We put the sun, and we imagine that there is this something, this fabric that is there everywhere. Well, the sun should interact with the fabric that is everywhere. And one way to interact is to bend it, to change the shape of the fabric around the object. We don't see it. There's no fluid, there's no water, there's something that is all around the universe that we could feel. That's true. But the person who came up with this idea called that fabric space-time, because it is made of space and time. And according to his crazy idea, space and time get distorted around objects like stars, like planets, like everything. And he called this gravity. For him, gravity is the distortion of space and time around objects and energy in our universe. The guy who came up with this crazy idea is called Albert Einstein. And what I've just described to you is what we call the general theory of relativity. It is a theory of gravity. It says that every object, every energical thing that exists in our universe bends, distorts space and time around it, creating gravity. Einstein published all this in 1915. 4 years later, there was a total eclipse of the sun off the coast of Africa. And one man called Eddington from Cambridge University decided to travel to that island off the coast of Africa to look at the eclipse. If Einstein was right, then when the sun is eclipsed by the moon, you can see the stars that are around the sun. And if Einstein was right, these faraway stars should not be where they are. Eddington did that experiment, did that expedition, and he saw that Einstein was correct. Light is bent by matter. Space-time is bent by energy. Gravity is a bending of space-time. So, all of a sudden, we have a theory of gravity. Gravity, according to this, let me summarize, it says the following. It says that our universe has a geometry around every object. Space and time are bent around everything. So Einstein's theory is one of the most beautiful theory ever for one reason. It equates two things that had nothing to do with each other before he came along. These two things are geometry on one side and energy on the other. Einstein's theory says that the geometry of space and time is equal to the matter that is and the energy that is in our space and time. Good. That's an equation. That's a formula. Do we have solutions? To have a universe that obeys Einstein's law, you must find a universe, as if it was easy, find a universe with everything that it contains, and it has to obey that formula, that the geometry that you find is the same as the matter and the energy that's inside. This is such a complex equation that Einstein himself thought that no one would ever find a solution. He published that equation in 1915. And in 1916, someone came up with a solution. Someone named Karl Schwarzschild. He found a solution of Einstein's equation that described a star alone in the universe. That was his solution. Einstein couldn't believe it. He did it. It worked. So, once you have something like this, what can you do? You can try and see what you can learn about an equation like that. For instance, you have your star, and you move it a little bit to see what that would create. Does that change anything? And it's extraordinarily easy to do and to see that if you wiggle it a little bit, you will see in your equation that you create a wave in space-time. It's exactly the same as if you had a small ball, solid ball, inside water. So you have to think about space-time as a fluid, and when things move inside that fluid, waves of space and time wiggle around. This is exactly what we call gravitational waves, waves of space and time. I'm sure you understand and imagine that to create a wave in space and time, you need a tremendous amount of energy. It's not just doing like this with my finger that would create a wave of space and time. All the energy from my finger when I do this goes into pushing the air that's around there and heating a little bit my finger. It's never going to do anything with space and time. So how do you get real gravitational waves that could maybe be felt? You need an enormous amount of energy. And this brings us to the limits of Einstein's theory. Black holes. Black holes, if you think about them, you can think about them from a Newtonian perspective. From Newton's perspective, gravity was a force. Fair enough. We know that's not the case anymore, but it was a force. And you also know what the trajectory of something will be if you throw it up. Now, it so happens that we know the mass of the Earth, so we know that starting from the Earth, if I want to throw something so fast that it reaches space, you need to throw at a certain speed. And we know that speed. It's about 42,000 kilometers per hour. If you throw something at 42,000 kilometers per hour, it will reach space and not come back. Imagine if the Earth is twice as dense as it is today, we would be like this. We would have a really hard time to walk. The gravitational pull would be so strong that you would need to throw things at a much higher velocity. For instance, the sun. If you want to leave the sun, you need to throw stuff at more than 2 million kilometers per hour. If you do less than that, it will go up, and fall back down on the sun. But we know some things go faster than 2 million kilometers per hour. For instance, light. Light travels at 1 billion kilometers per hour. So it can escape the sun. That's why we see the sun. If light was traveling slower than that, we wouldn't see it. And already by the time of Newton, there is a British scientist called Mitchell who came up with this idea that if you had something that was so dense, so massive, that you needed to travel at more than 1 billion kilometers per hour to escape into space, then nothing would ever come out of it, because light would not be able to escape. At the time, it was not called a black hole, but that's the idea of a black hole. So the idea was born already with Newton, that you have things that are so dense, so massive, that nothing can escape. And it so happens that Schwarzschild, the same guy who found out the first solution to Einstein's equation in 1916, found an equation, a space-time, a universe in which there are black holes. And in about 20 years later, in the 1930s, two scientists described a way for those black holes to be born. And they found that when a gigantic star explodes, it crushes its heart, what is inside it, so much that the heart becomes so dense that you reach the critical limit. It is so dense that it cannot do anything but collapse on itself. If I was standing on a black hole right now on the surface, the ground would fall down under my feet all the time. I would never reach the ground, actually. And my legs would be pulled down faster than my head, so that I would become spaghetti as I fall down inside. Black holes, according to all the theories we have, or let's define them this way, black holes are the opposite of emptiness. They are the extreme density that space-time can cope with. You cannot do anything that's more dense in energy or matter than black holes. Do they exist, black holes? Well, yes, they do. We see signs of them everywhere in our universe, everywhere. You probably know that we live in what we call a galaxy, which is an island made of about 300 billion stars, and that galaxies like ours is called the Milky Way, but there are loads of galaxies like that in space everywhere. We know of about 1,000 billion of them. And we also know that there is probably a supermassive black hole at the center of pretty much all the galaxies in the universe. When I say supermassive black holes, I'm talking about black holes that are more than a few million times the mass of the sun. The black hole at the center of our galaxy is about 4 million times the mass of the sun. The biggest black hole we've ever detected is about 15 billion times the mass of the sun. They're enormous beasts that swallow everything that goes by and grow bigger all the time. What did we know about them? We kind of knew they could be created when giant stars explode. We kind of know that there are gigantic black holes at the center of galaxies, but we didn't quite know how to get from one to the other, how you get from a small, tiny one to a huge one. So one possibility is that black holes could merge. Small black holes could collide into one another and become a bigger one, and then collide again and become a bigger one again and again and again. Some people started doing calculations about this possibility in the 1960s. There is a scientist called Thibaut Damour who specialized in doing these calculations in the 1960s. And what he found is that when two black holes start moving around one another, they will spin, they will swing faster and faster and smash against one another. This collision by far would be the most powerful explosion or collision or energetic release or whatever you want to call it, the most powerful thing that exists in our universe. So powerful that it would shake space and time, that it would shake it by creating waves. Those waves that Einstein predicted in 1916, those waves that would propagate in space and time and go far away at the speed of light. But we had no way of detecting these. You need a special detector to do that. I mean, as of today, or until, let's say, a couple of years ago, the only tool we had to probe our universe was light, electromagnetic waves, the thing that our eyes can detect, plus UV light, X-rays, but all this thing is about electromagnetism. This, gravity waves, it's not light. Our eyes can't detect it. Our detectors could not detect it. You'd need something that would detect what? A wave of space and time? But what does that mean? If I have a gravity wave passing through me now, what does it mean? Well, it means my size will go whoop, 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 and come back to normal. Same for my watch. The way time goes, flows, would change. As the wave passes through me, time will slow down, accelerate, slow down, and go back to normal. Has any of you ever felt a gravity wave pass through you? I guess you must have, a few of you must have felt that. Now, it's impossible. It's too small. The change in size, not only it's too small, but if it happens to me, it happens to you as well. Now, for some decades now, a group of scientists have dedicated themselves to trying to build a detector for these waves. I think it was around the 11th of September 2015. They switched it on, they waited for a day, second day, third day, and the third day, at around 9:52 a.m. Universal Time Zone, they detected something. 3 days only after switching their detector on, they saw a wave of space and time pass through them. 2 detectors were on at the time. They're called LIGO in the United States, and both of them saw the signal. So we knew there was a gravitational wave that passed through. To give you an idea of how powerful that is, that's about the equivalent of 50 times the power of all the stars in the universe combined that was released from that spot where the 2 black holes collided. This collision happened a long time ago, about 1 billion years ago, and it took that time for it to reach us. That's why the signal was tiny. But if you picture yourself being next to that collision, what would have happened to you? Well, your size would have changed by about 13%. And that's a lot. That's a few centimeters. Everything would be distorted around it, that so much that you could see it things, everything from space and time would have been distorted. This detection of gravitational waves is, from my point of view, one of the most important experimental achievements mankind has done since Galileo with respect to the cosmos and things like that, obviously. Why? Before gravitational wave detectors, we only had light to look at the sky, nothing else. Everything we tried to understand about nature, about the history of the cosmos, about where we come from, about what may happen in the future, was done using light signals or electromagnetic signals coming from space. Nowadays, we have a new tool. And if we're lucky, we will even be able to look at one event with the two tools we have now: gravitational waves and normal telescopes that would look at the light that comes out of it. That's exactly what was announced to have happened on Monday, the 18th of October. We've had, for the first time, a detection of both visual and gravitational waves of something that created gravitational waves somewhere far away in space. What was detected this time? Not two black holes colliding. What was detected is two neutron stars colliding. If you want a scale of extreme objects in space, neutron stars are on the podium. Black holes are number one, and then you get neutron stars. In the matter we are made of, there are atoms. Inside atoms, you have nuclei, electrons and nuclei. Inside the nuclei, you have protons and neutrons. A neutron star is a star made of neutrons, the stuff that's inside the core, the nuclei of atoms all around us. It's extraordinarily dense. The collision of two neutron stars was spotted, both because they're so energetic that they released gravitational waves, and they're so energetic that they also release light that was caught in our telescopes in the European Southern Observatory in Chile. The first detection of gravitational waves told us that intermediate-sized black holes, about some dozen times the mass of the Sun, exist, and they can smash into one another to create a bigger one. That's cool. Then it opens up a new era in astronomy because we're looking at stuff we couldn't see before. Well, when we watched the two neutron stars collide, we saw that such a collision created the heavy elements we are made of. So basically, most of the gold you may have in your necklaces or rings or watch, the gold was created, was assembled, was forged during the collision of two neutron stars a long time ago. The other thing that we managed to see thanks to this collision is that gravitational waves and gravity travel pretty much at the same speed as the speed of light. And that means that we be able to rule out some strange theories about our universe that were brought in to explain dark matter, for instance. These gravitational wave detectors, they are basically giving us a new eye to look at the universe. So, for instance, the two black holes that collided, they actually collided a billion years ago. But we saw it now, because they were very far away, and it took that time for the signal to reach us. That using the usual telescopes we had up until gravitational wave detectors, we could not see further than 3,000 years. But with gravitational waves, yeah, we may. We may be able to, because gravity waves can travel through anything. So the future generations of gravitational wave detectors, they may allow us to have a look through gravity waves at what happened up to the very beginning of space and time. And for any of you who may want to do physics or start doing research, I believe this is a very, very exciting time. There are many discoveries to be made in this subject. And I thank you very much for listening to me. 谢谢。